We use one cell in an electric circuit to understand the concept of EMF and internal resistance of a cell. We will now look at different combinations of cells and conceptualize an equivalent EMF and equivalent internal resistance for these combinations, just as we did in the case of resistors in series and in parallel combinations. Cells are connected either in series or in parallel combinations to obtain the required voltage and current in a circuit. To calculate currents and voltages in a given circuit, the combination of cells is replaced by an equivalent cell that gives the same EMF as that of the combination. First, let us consider a combination of two cells that are connected in series. One terminal of each cell is joined together, leaving the other terminals of the two cells free. There are two ways to make a series combination of two cells. In the first way, the negative electrode of the first cell is connected to the positive electrode of the second cell. In the second way, the negative electrode of the first cell is connected to the negative electrode of the second cell. Let us now analyze the first case, where the negative electrode of the first cell is connected to the positive electrode of the second cell. E1 is the EMF of cell 1. R1 is the internal resistance of cell 1. E2 is the EMF of cell 2. R2 is the internal resistance of cell 2. The potential at point A is VA. The potential at point B is VB. The potential at point C is VC. VAB is the potential difference between points A and B, which also represents the potential difference between the positive and negative terminals of the first cell. We know that terminal voltage V is equal to E minus I into R. Substituting the corresponding expressions of cell 1 in this equation, we can now write VAB is equal to E1 minus I into R1. Let this be equation 1. Similarly, for the second cell, we can write VBC is equal to VB minus VC is equal to E2 minus I into R2. Let this be equation 2. We can now write the potential difference between the terminals A and C of the combination of cells as VAC is equal to VA minus VC, which is equal to VA minus VB plus VB minus VC. Substituting from equations 1 and 2, we have VAC is equal to E1 minus I into R1 plus E2 minus I into R2. Rearranging and simplifying the right side of the equation, we have VAC is equal to E1 plus E2 minus I into R1 plus R2. Let this be equation 3. Writing equation 3 in the form V is equal to E minus I into R, we get VAC is equal to EEQ minus I into REQ, where EEQ is the equivalent EMF and REQ is the equivalent internal resistance of the combination of the cells. Let this be equation 4. Comparing equations 3 and 4, we can write EEQ is equal to E1 plus E2. Let this be equation 5. Req is equal to R1 plus R2. Let this be equation 6. Equation 5 is used to calculate the equivalent EMF of the series combination of two cells. Equation 6 is used to calculate the equivalent internal resistance of the series combination of two cells. Let us now observe changes in the equations when the negative terminal of the first cell is connected to the negative terminal of the second cell and E1 is greater than E2. Let us call this case 2. We will now proceed with the derivation just as in case 1. As E1 is greater than E2, current I leaves the positive terminal of the first cell, goes through the external circuit and moves from the positive terminal of the second cell to its negative terminal and finally reaches the negative terminal of the first cell. The current leaves the second cell from its negative terminal. As the direction of the current I within the second cell is opposed by its EMF E2, E2 is taken as negative in the equation for VBC. Hence, we get VBC is equal to minus E2 minus I into R2. Let this be equation 2. Writing the equation for VAC. By substituting equations 1 and 2, simplifying and putting it in the equivalent form, we get EEQ is equal to E1 minus E2. Let this be equation 5. From equations 3 and 4, we can write Req is equal to R1 plus R2. Let this be equation 6. We can now extend these rules to any number of cells in a series combination. Rule number 1. The equivalent EMF of a series combination of n number of cells is the algebraic sum of their individual EMFs. If, in the combination, the current leaves any cell from the negative electrode, the EMF of that cell will bear a negative sign. Rule number 2. The equivalent internal resistance of a series combination of n number of cells is the sum of their internal resistances irrespective of the orientation of the terminals of the cells in the series combination. Let us now consider a parallel combination of two cells. The positive terminals of the two cells are connected to each other. Similarly, the two negative terminals are connected to each other. I1 is the current leaving the positive electrode of the first cell. Similarly, I2 is the current leaving the positive electrode of the second cell. At junction point B1, I1 and I2 flow in and flow out as I into the external circuit. At any point in a circuit, the total charge flowing in must be equal to the total charge flowing out. So, at junction point B1, we can write I is equal to I1 plus I2. Let this be equation 1. VB1 is the potential at point B1. VB2 is the potential at point B2. the potential difference between points B1 and B2 taken across cell 1 can be written as V is equal to VB1 minus VB2. V is equal to E1 minus I1 into R1. Rearranging the terms, we can write I1 is equal to E1 minus V divided by R1. Let this be equation 2. Similarly, taking points B1 and B2 to be across cell 2, we can write V is equal to VB1 minus VB2. V is equal to E2 minus I2 into R2. Rearranging the terms, we can write I2 is equal to E2 minus V divided by R2. Let this be equation 3. Substituting equations 2 and 3 in equation 1, we get I is equal to E1 minus V divided by R1 plus E2 minus V divided by R2. On simplifying and rearranging the terms, we get I is equal to E1 by R1 plus E2 by R2 minus V into 1 by R1 plus 1 by R2. By further rearranging the terms, we can write V is equal to E1 R2 plus E2 R1 divided by R1 plus R2 minus I into R1 R2 divided by R1 plus R2. Let this be equation 4. We can replace the combination of two cells with one cell of EMF, EEQ, and internal resistance, REQ. We can now write V is equal to EEQ minus I into REQ. Let this be equation 5. From equations 4 and 5, we can write EEQ equal to E1 R2 plus E2 R1 divided by R1 plus R2. Let this be equation 6. REQ is equal to R1 R2 divided by R1 plus R2. Let this be equation 7. Equation 7 can be written as 1 by REQ is equal to 1 by R1 plus 1 by R2. Let this be equation 8. Dividing equation 6 by equation 7 and rearranging the terms, we get EEQ divided by REQ is equal to E1 by R1 plus E2 by R2. Let this be equation 9. In the circuit that we used, two positive terminals are joined to each other, and similarly, two negative terminals are joined to each other, and currents I1 and I2 are flowing out of the positive terminals. If the negative terminal of the second cell is connected to the positive terminal of the first, equations 8 and 9 are still valid by replacing E2 with minus E2. Equations 8 and 9 can be extended when n cells of EMF E1 to En with internal resistances R1 to Rn are connected in parallel combination. They can be replaced with a single cell of EMF EEQ and internal resistance REQ. We can write 1 by REQ is equal to 1 by R1 plus 1 by R2 plus and so on up to 1 by Rn. EEQ by REQ is equal to E1 by R1 plus E2 by R2 plus and so on up to En by Rn.